introduce you?
What? Say again?
Ready? Can you introduce you?
Yeah, yeah.
Okay, hello again, everyone. For the afternoon session, we are happy to start with Hans Ringstrom from KTH, who is going to tell us about Quiescent Big Bang Singularities.
Okay, so thanks a lot. Thanks a lot for the invitation. It's a great pleasure to be here at the Fields Institute. I'm enjoying my stay very much. So the topic of this talk is Quiescent Big Bang Singularities. In order to give a background, I will do this very briefly. It's going to be rather similar to what Warren did this morning, right? So you start with the singularity theorem by Hawking, telling us that generically we should expect cosmological solutions to have singularities in the sense of time-like geodesic incompleteness. But as Warren pointed out, we don't know much about the nature of these singularities. So it's not so clear, do curvature invariants blow up as you follow an incomplete time-like geodesic? What about strong cosmic censorship? Do initial data generically, uniquely determine the maximal development and so on, right? So the nature of singularities is sort of unclear. And then if you want to know about the nature of singularities, it's natural to turn, like Warren did, to the BKL conjecture. And according to this conjecture, very roughly speaking, singularities are expected to be space-like in the sense that different observers going to the singularity lose the ability to communicate. They're expected to be local, so each observer experiences its own little spatially homogeneous universe, and the models for this spatially local behavior are these oscillatory spatially homogeneous solutions that Warren was discussing this morning. But there are certain matter models in which these oscillations are suppressed, and that also in higher dimensions they're suppressed, and also under certain symmetry conditions they're suppressed, and the behavior is then convergent instead, or quiescent, right? And this talk is about this quiescent setting, right? But this is still rather vague. So what does one really mean by convergence? In what sense do these solutions actually converge? And if the solutions converge in the direction of the singularity, can you think of the limits as some sort of initial date on the singularity? So the thesis of this talk is that there is a natural geometric notion of initial date on the singularity, and that this notion can be used to give sort of a unified perspective on these quiescent Big Bang singularities. But let me start with this question. In what sense do quiescent solutions converge? And let's look at model solutions. Again, this will be familiar. So, so first of all, in order to do this, I of course have to make a choice of matter model. In this talk, I'm going to focus on the Einstein scalar field equations that I expect many of you are familiar with. Most of the results also hold in the presence of a potential, so the Einstein nonlinear scalar field equations, but these are the equations I'm mainly going to be discussing here today. And now one sort of model behavior, or one model solution describing this convergent behavior are these solutions that I've written on the board here. So these are spatially homogeneous and spatially flat solutions to the Einstein scalar field equations, right? So here, the underlying manifold is 0 infinity across the n torus, or Rn if you prefer. The metric is given by this expression here. Okay, so the metric is given by this expression here. And so the t is just the variable on 0 to infinity. The pi's are just constants. The dxi's are just the standard one forms on the n torus. And the scalar field is just a log t plus b, where a and b are constants, right? So if these constants satisfy these relations, this is a solution to the Einstein scalar field equations. And this, okay, so this is, in a sense, you may say, rather a random, not so interesting solution to these equations, but this is really the model for the behavior that observers should experience going into the singularity, right? But it would be nice to have sort of a more geometric understanding of these solutions, right? So so it's a more natural geometric way to characterize the solution. And if we want to extract some sort of data in the direction of the singularity, we certainly should be able to do it in this setting, right? What would be the data on the singularity for these solutions? And if you look at the solutions, it's not completely obvious because the scalar field is blowing up. I mean, it's going to infinity at the singularity. If you look at the components of the metric, they're either going to 0 or to infinity, right? So it doesn't look so promising if you want to extract some limit as time tends to 0 here. Okay, but so let's think about them in a geometric way. So here there is a foliation, of course, by the constant T hypersurfaces, and you may say, well, this is just some random coordinate. But in this setting, the constant time hypersurfaces are not just some random hypersurfaces. These are constant mean curvature hypersurfaces. And these constant mean curvature hypersurfaces are uniquely determined by the space-time. There's no freedom at all there. They are uniquely determined by the space-time, right? So this foliation is not a random foliation. It's a canonical foliation, which is determined by the space-time. There's, in that sense, no freedom there, right? Okay, so now if you want to extract data in the direction of the singularity, it's natural to look at data, initial data for the Einstein scalar field equations on each constant T hypersurface, and then try to take a limit, right? Okay, so what are initial data? So initial data for Einstein's equations is, of course, the induced metric, the induced second fundamental form, the induced scalar field, the induced normal derivative of the scalar field. These are the 4 things which are, this is the geometric data on a constant T hypersurface. So if we start with the geometry, it's the induced metric. So that's this, that's H. So this is the induced metric on a constant T hypersurface. And then I represented the second fundamental form as a 1-1 tensor field instead of as a covariant 2 tensor field here. But I mean, that's you know, that's just a choice, right? So I'm representing it now as the shape operator or 1-1 tensor field here. Okay, fine. And now you still see this problem that, I mean, the Weingarten map, the coefficients there are going to infinity, and you have this problem in the metric. But for the Weingarten map, there is actually one very simple geometric operation that you can do. If you take the Weingarten map and you divide it by the mean curvature, so the mean curvature is the trace of the Weingarten map. In this case, the mean curvature is 1/t, right? So if you divide the Weingarten map by the mean curvature, this is a perfectly general geometric operation, then you see that the resulting object actually doesn't depend on time. So that's one nice feature of this object. Another nice feature of this object is that now you see that these constants, the pi's, which seem perhaps a little bit random here, there's a natural geometric interpretation of these constants. These constants pi are the eigenvalues of the expansion normalized Weingarten map, right? So you should think of the pi's as the eigenvalues of the expansion normalized Weingarten map. This is a sort of natural geometric way to think of these objects. And then, okay, so here you have the dxi forms, again, slightly random objects. But these dxi's are not random objects. They just correspond to the eigenspaces of the expansion normalized Weingarten map corresponding to these eigenvalues pi, right? So all of these objects are very natural geometric objects from that point of view. Okay, so this is sort of the straightforward thing, the Weingarten map. Now, what about this? The metric? So the metric looks a lot worse, right? Because there, I mean, here we could just divide by a function and then we get something nice. That's not going to work for the metric. We need to do some sort of anisotropic rescaling of this metric in order to get something meaningful, to get a meaningful limit, right? So that's unpleasant in a sense. But on the other hand, again, if you now, with these observations I just made, if you look at this thing again, you see what are the exponents here? Well, the pi's, these are the eigenvalues of the expansion normalized Weingarten map. The directions, the dxi's, these are the eigenspaces, right? And what is the amount by which you're contracting or expanding? That's t. Well, t is 1 over the mean curvature. All of these things are perfectly geometric, right? So, so it's actually quite natural to introduce this expansion normalized metric, right? So you take little h, well, okay, so that's the induced metric. But now I'm introducing this expansion normalized metric script h, where I've introduced this theta raised to script k in front of x and y. Okay. So if you look at this the first time, it may look a little bit funny because script k is a 1-1 tensor field. So I'm raising a function to 1-1 tensor field, and this may feel uncomfortable. But the point is that since it's a 1-1 tensor field, it's an endomorphism of the tangent spaces of the leaves of the foliation, right? So in coordinates, it's like a square matrix, right? And we know how to exponentiate square matrices. It's not more complicated to exponentiate a 1-1 tensor field, right? That's perfectly fine. You just define it, I mean, just like you would for a matrix exponential, right? So there's nothing strange there. So theta raised to script k, this is a perfectly nice, smooth 1-1 tensor field. There's nothing strange about this, right? So this is perfectly natural. And if you apply this definition for these Kastner solutions, what happens is that this script h is just the flat Euclidean metric. That's the only thing that's left here. So now there is no time dependence left here either, right? So script k is independent of time, script h is independent of time, right? So that's fine. And note also, I mean, both of these definitions, both the expansion normalized Weingart map and the expansion normalized metric, these objects, the definitions are perfectly general and geometric, right? Okay. So now we need to do something similar for the scalar field. And the scalar field is actually easier. So the time derivative of the scalar field is going to blow up. But if you expansion normalize it, so here u is the future directed unit normal to the constant Ti per surfaces. This is just d by dt in our case. So then u phi is the normal derivative, but then this is going to blow up. But if you expansion normalize by dividing by the mean curvature, this is perfectly fine. And then for the scalar field, you have to sort of subtract the leading order term, which is geometric, and then you get this capital phi. So both of these definitions, capital psi and capital phi, are perfectly general, perfectly geometric definitions, right? And in this particular model case, the objects you end up with, well, they are constant, right? So in this case, for the case of this scalar field, phi is a log t plus b, these objects are just constants, right? Okay. So to summarize, in this setting, if you apply this geometric expansion normalization, what you end up with is this script k, script h, capital phi, and capital psi, right? And these objects are now, they have perfectly geometric definitions, general definitions. They are independent of time, so certainly you can take the limit as t tends to 0. So you can think of these things as data on the singularity in that sense, right? And then, I mean, the only thing you have to put in beyond this data is the mean curvature to get the actual solution, right? I mean, if you put the t back in, you get the actual data induced on the constant Ti hypersurfaces, right? Okay. So this is one way to sort of extract a limit in the direction of the singularity, and this gives you then a notion of initial data on the singularity, because this data now uniquely determines this solution. But okay, but this was just a model case. It's an important model case, but it's a model case. And now, but on the other hand, you can apply it more generally. So let's apply it more generally. Okay, so here, let's now say that we have instead a crushing singularity. So we have a space-time, mg, so time-oriented Lorentz manifold. And I'm going to assume here that m is just sigma cross I, where I is an interval. I'm going to assume that the constant Ti hypersurfaces are some space-like Cauchy hypersurfaces. I'm going to assume that the mean curvatures of these constant Ti hypersurfaces is blowing up uniformly as t goes to t minus, right? So this is the type of situation I have in mind. This is sort of what you would have in mind from Hawking's theorem anyway, right? I mean, this picture you would have in mind. Okay. But now, and I'm going to assume also that mg phi is actually a solution to the Einstein scalar field equations. So I'm going to assume that this is a solution to the Einstein scalar field equations. And so in this setting, on each constant T hypersurface, you get induced data for the Einstein scalar field equations. So the induced data are so the induced metric, induced second fundamental form, induced scalar field, induced normal derivative of the scalar field. And you can do this since the mean curvature is blowing up uniformly, the mean curvature is strictly positive. So you can definitely define all these expansion normalized quantities here. So all of these quantities are perfectly fine, right? And now you can ask yourself the question, do these objects have a limit in the direction of the singularity, right? So in our model case, these objects were constant, so clearly there was a limit. But it turns out that, and there are situations in which there are no limits. So for instance, when you have this oscillatory spacetimes, then you're not going to have limits of these objects, right? So there are certainly cases where you don't get a limit. But there are also quite natural conditions where there are limits. So the main objects are really the script k and the capital psi here, these objects, right? So there are general assumptions. I don't want to go into the details, that's somehow a separate talk, but there are sort of some general, rather natural, in my opinion, assumptions, mainly focusing on this script k and capital psi. So these objects, that the expansion normalized normal derivatives of these objects should decay at some rate, then you can prove that these objects converge. So you don't assume that script h and capital phi converge, but you can then deduce that script h and script phi converge. And not only do they converge, in fact, so first of all, they converge. So under suitable assumptions, you can conclude that these objects converge to limits. But not only do these objects converge to limits, these limits also satisfy certain conditions. They are what I call initial data on the singularity, right? In the following rather precise sense. So what are, I'm going to focus on the non-degenerate case in this talk. You could define also in the degenerate setting, but so sigma, script h ring, script k ring, phi ring, and psi ring, these are non-degenerate initial data on the singularity. If, first of all, sigma script h ring, this would be a Riemannian manifold. Script k ring should be a 1-1 tensor field. Phi ring, psi ring should be smooth functions. You can define this in other degrees of regularity also, if you prefer. Then there's a list of conditions here. So the trace of script k ring should be 1, and then script k ring should be self-adjoint with respect to the script h ring. You have these equations here. So these you should, roughly speaking, think of. So this is the limit of an expansion normalized version of the Hamiltonian constraint. And this thing is sort of a limit of an expansion normalized version of the momentum constraint, rather roughly speaking. There are some cancellations going on here, right? I will here assume that the eigenvalues of this script k ring are distinct. This is not absolutely necessary, but in this talk, I'm going to focus on the case that these eigenvalues are distinct. And then there's the fourth condition, which is, the most technical one, but on the other hand, perhaps the most interesting one. So this requires some extra explanations here. So what is this OABC? So let now PA ring, these are the eigenvalues of this script k ring. And the XA ring are corresponding eigenvector fields, which have been normalized with respect to this metric H ring. So this condition determines PA ring uniquely, of course, the eigenvalues. And it also determines the XA ring up to flipping a sign. So minus XA ring will satisfy the same condition as XA ring. But that's the only freedom you have left still, right? Now, given these objects, what turns out to be important are the structure coefficients of the eigenframe of the limit of the expansion normalized Weingart map. These structure coefficients turn out to be crucial players here. And they are well-defined up to a sign. That's why I'm squaring them here. So these objects are now globally well-defined objects, right? These OABC. And the condition here is that this quantity OABC has to vanish in a neighborhood of X if this inequality holds. Right? And so let me perhaps make some so the point is, so Warren was pointing out that sometimes you have this negative eigenvalue. So in 3+1 dimensions, so first of all, when B equals C, OABC is automatically 0, right? Because it's a structure coefficient here, right? So B this condition is sort of void when B equals C. It's only relevant when B is different from C. And it also turns out that, I mean, because of these conditions, A, B, C, they sort of all have to be different in order for this to happen, right? And in 3+1 dimension, this just corresponds then to PA less than equal to 0. That's what this condition corresponds to in 3+1 dimensions, right? So that's a problematic case. And so in that case, you would sort of expect a bounce, like Warren was talking about this morning. But the mechanism causing the bounce is really the structure coefficient. So you're turning that off, right? So you turn this off to avoid the bounce and to get quiescent instead of oscillatory behavior.
The PAs have no, suppose you were going to a catheter.
Yeah, yeah.
The PAs have no connection with the catheter exponent.
Well, I mean, they are effectively the Kastner exponents. Right?
Because I thought that's always one. Right? They sum up. They all sum up to.
But they sum up to 1, yes. But this, so the thing is, that means that 1 minus PB minus PC is PA. So the left-hand side is 2 PA then, right? Right. Okay. It is 1 plus PA minus PB minus PC. Yeah, yeah. Okay. So right. And so the thing is that, so if this combination of eigenvalues is always strictly positive when B is different from C, this is called a subcritical case. That's a subcritical case. So when this expression is strictly positive for B different from C, right? That's the good situation where you don't really need, then you don't need this condition. That goes away, right? Okay. Okay, good. So this is now a notion of initial data on the singularity. If you see it for the first time, well, maybe you don't like it, maybe you like it, I don't know. But maybe it's an acquired taste, I don't know. But by now, I like it a lot, right? So if you look at this for long enough and you see sort of how it fits together with the Big Bang singularities, you will, I hope, come to like it, right? So first of all, this notion of data on the singularity is geometric, right? So I mean, if you have two quintuples or whatever like this, and they are isometric, and one of them is data on the singularity, while the other one will also be data on the singularity. So it's meaningful here to speak of, I mean, all the conditions are geometric here. So it's meaningful to talk of isometric data, you know, two initial data sets on the singularity being isometric and so on and so forth. And since Einstein's theory is a geometric theory, that's a very desirable feature, right? So that's one thing, right? So they yield a geometric initial value problem, starting with sort of geometric data on the singularity. And there is actually, in the 3+1 dimensions, there is a result saying that there is a corresponding maximal development, somehow, unique maximal development. Hopefully I get to that towards the end, right? So there's a geometric initial value problem. This perspective that I've just described, there's a large body of work starting with data on the singularity, and this notion of data on the singularity gives a unified picture of those results. So that's another advantage. Also, I mean, there are lots of different results in symmetric settings where we look at symmetric metrics and we try to understand what are the asymptotics in the direction of the Big Bang. Again, this gives a unified picture of that, because what solutions do generically is they converge to data on the singularity, right? So that's what happens. And also, this perspective gives natural conjectures concerning the asymptotic. So if you would take just the Bianchi class A models, for instance, right? So you take a left invariant initial data on unimodular Lie group, and then you look, what are the asymptotics? Well, then you can first calculate what are the asymptotic data in that setting. That's a purely algebraic problem. And then the natural conjecture is, well, the solutions should converge to data on the singularity. This is what happens, right? And for instance, in the case of Bianchi 8 and 9 vacuum spacetime, then you can verify there are no data on the singularity, right? And if there are no data on the singularity, you expect the solution to be oscillatory. Well, that's exactly what happens, right? So you can use this perspective to generate conjectures concerning what the behavior solutions should be, right? So in that sense, it also gives natural conjectures. But the result I want to focus on today is that solutions that induce subcritical non-degenerate data on the singularity are robust. Right? So that such data is actually an attractor. So what do I mean by that? So if I have a solution inducing subcritical non-degenerate data on the singularity. And if I perturb regular data of that solution, the corresponding development will also induce subcritical non-degenerate data on the singularity, right? So that this is an attractor for the dynamics, right? So that's the result I want to focus on or start with presenting, and then time permitting, I will talk about some of the other points. Okay, so before I speak about this result, it's natural to say a few words about results on stable Big Bang formation. And I mean, until recently, there were not so many results on stable Big Bang formation. So what do I mean by stable Big Bang formation? You have a solution, typically spatially homogeneous solution, inducing a Big Bang. And then you ask yourself the question, if I perturb the corresponding initial data, do I still get a solution with a Big Bang, right? So that's stable Big Bang formation. Until very recently, there were no results in this direction whatsoever. So the first result came some 10, 15 years ago, but it was published 2018. So this is this work by Igor Rodniansky and Jared Speck. And then after that, there's been a large body of work here. So, and this is an incomplete list, and I'm certainly not going to describe all of these different results. But, but gradually, I mean, there are less and less symmetry and various types of matter models being included here. And also there's a parallel story, so to speak. So many of the results are in this CMC setting. So you have constant mean curvature foliation. But it would also be nice to localize, localize in space. And this has been sort of pioneered by Florian Bayer and Todd Olenek, and also later other collaborators. So there's a large body of important work here. The result I really want to focus on here, I just want to mention specifically, is this one by Fomodovlos, Rodniansky, and Speck, right? So this result was very important in that they proved stability for all of these model solutions I described earlier, for which you would expect stability. So it's really a natural sort of maximal result. All the subcritical solutions are stable. I mean, these model solutions, spatially homogeneous and spatially flat model solutions, all the subcritical such solutions, they're stable. So that's the first thing. But what was also very important in this paper, they introduced new methods, a new set of equations, a new perspective, which turned out to be extremely fruitful and which has sort of had a big influence on the development of the field, and somehow also certainly this result I'm going to present today, like the ideas in this paper were very important. Okay, so these are important and very nice results. One complaint, or okay, I have a few complaints, otherwise I wouldn't be here, I suppose. So one thing is that the results, you start with specific spatially homogeneous solutions to the equations, and then you have to start with initial data that are close to specific spatially homogeneous data, right? And now it would be much nicer to have a general conditions without any reference to a background solution, right? I mean, in the spirit of Hawking's theorem, you have some general condition which ensures that you get Big Bang formation and curvature blow-up, right? This is what you would like to prove, and not have any reference to a background solution. So that's one thing. And the other thing you would like to have, you would like to prove that these solutions actually induce data on the singularity in the way I described, right? So these two things you would very much like to have, right? So the result, I think some of you, a few of you have probably heard me speak about the first paper where we do some of this. But what I want to talk about today is actually more the second paper, which is joint work with Andres Franco-Grisales. Right? So in this case, we actually prove that we get data on the singularity. Right? So what is the result? So I'm going to be interested. So this result is again about in the CMC setting. So I'm considering initial data sets for the Einstein scale of field equations. And I'm assuming that they have constant mean curvature, which is positive constant mean curvature, right? And now, given this initial data, I can define this expansion normalized data just the way I explained a few transparencies ago, right? So you get these, given these initial data, so this is just sigma, little h, little k, little phi, little psi, right? And then you can, from that, you get these expansion normalized data, right? Just according to the definition I just gave, right? Okay. And then the type of data I'm going to be interested in here is such that if PA is now the eigenvalues of this expansion normalized Weingarten map, and sigma P is a parameter, I'm going to assume that I'm in the subcritical regime, so that this inequality holds, and there is some small parameter sigma P here, right? So I expect something like this to be necessary because, I mean, if this object here is less than equal to 0, then you expect instabilities to be important, right? So you sort of expect something like this to be necessary. Sigma P can be arbitrarily small, but the argument depends, certain aspects of the argument depend on the size of the sigma P. I mean, so P, so the thing is that P are functions on sigma, right? So the thing is that you have, say again? Okay, sorry. No, sorry. Well, I mean, I'm looking at, okay, so I'm fixing a parameter sigma P, okay. And now I'm looking at initial data sets satisfying this condition. That's, yeah, so this is an open set, right? Okay, good. So this is the type of initial data I'm interested in. And now, so what is the condition I want to impose here? So given these parameters, there's then a natural number kappa, which only depends on the spatial dimension of the manifold and on this parameter sigma P, such that the following holds. So I'm going to just read this, and then we're going to contemplate this for a minute. So if you give me theta 0, so you give me a large real number theta 0, what I will give you in return is another large real number, theta 1, so that if these expansion normalized objects are bounded by theta 0 in these sublet norms, the distance between the eigenvalues is bounded from below by 1 over theta 0, and the mean curvature is bounded from below by theta 1, then I get a big bang with curvature blow up. Right? Okay. So this is the statement, but this requires, I mean, so this is slightly technical, so I think it's worth pausing a moment to contemplate these conditions, right? And I think it's natural to view these conditions in sort of with this notion of solutions inducing data on the singularity in mind. So assume now for a moment that we actually have a solution that induces data on the singularity, right? Then we have not only one initial data set, we have a family of initial data sets, right? And the expansion normalized quantities are supposed to converge in the direction of the singularity. In that case, the left-hand side here is actually parameterized by the leaf of the foliation, right? But if the solution induces data on the singularity, the left-hand side is converging to something, right? This can be extremely big, but it's converging to something, right? So this is converging to something. If the eigenvalues on the singularity are distinct, then sooner or later there will be a uniform positive lower bound on the distance between the eigenvalues. So that's also going to be satisfied, right? So as you now go towards the singularity, these objects will be uniformly bounded. These things will be uniformly bounded from below. But while these are uniformly bounded, the mean curvature is blowing up, right? So this lower bound here on theta 0 is no problem, right? Because just going close enough to the singularity, theta 0, the initial mean curvature is going to be bigger than whatever constant you prescribe, right? So any solution inducing data on the singularity will satisfy this criterion, right? So this is not just some random criterion. Any solution inducing data on the singularity will satisfy this criterion, right? Okay. So this is, from that point of view, this is a natural assumption. So what now are the conclusions if you make this assumption? Okay, so if you look now at the maximal global hyperbolic development of this initial data set, then the causal past of the initial hypersurface will be foliated by CMC hypersurfaces. And the range of the CMC, the mean curvatures, will go from the initial mean curvature all the way up to infinity, right? So you will have a crushing singularity in that sense. The mean curvature will blow up, right? Second, there are initial data on the singularity, so non-degenerate initial data on the singularity, and actually subcritical non-degenerate initial data on the singularity, if I'm going to be very precise, so that these, so script h of t, this is the expansion normalized metric on the hypersurface of constant mean curvature 1 over t, right? So the t parameterizes, so 1 over t is the mean curvature in this setting. And so the t parameterizes the constant mean curvature hypersurfaces, and script h of t is the expansion normalized metric on the hypersurface of constant mean curvature 1 over t, right? And similarly, you know, they have the expansion normalized Weingarten map and so on. These objects converge in any CK norm to the data on the singularity with a rate, right? So this is a consequence you get out of this. And then the curvature blows up. So note that this setting actually includes the vacuum setting. So if you have vacuum solutions to Einstein's equations, this is included, but then you have to be in 11 or more space-time dimensions in order for this subcriticality condition to be consistent, right? But so, and of course, if you're in vacuum, the Ricci tensor is not going to blow up. But if this psi ring is non-zero, then the space-time Ricci tensor contracted with itself is going to blow up in the direction of the singularity. And irrespective, the space-time Riemann curvature contracted with itself, so the Kretschmann scalar, this is going to blow up in the direction of the singularity, right? And then all causal geodesics are passed incomplete. Okay. So this is the result. Okay. So let me sort of list some aspects of this.
Can I just ask a question about your second one?
Yeah.
Do you have any idea, like, do you have any control on how big you have?
Okay, that I don't have. Not in my head. No. I would probably have to go through the papers, and then, yeah, it's going to be a mess, right? Yeah, I would expect. Yeah. I mean, because I mean, it's lots of estimate after estimate, and you have to somehow. Yeah. Okay. Okay. Good. Right. So note here that in this result, there is no reference to any background solution. I mean, it's a general condition on initial data, not giving any reference to any background solution, right? And the result, it also holds in the case of the Einstein nonlinear scalar field equations. And in the case of the Einstein nonlinear scalar field equations, there are lots of situations where you have future global nonlinear stability. And if you combine the two, you get for large classes of solutions, past and future global nonlinear stability. And then, I mean, and the point is then, as I said, I mean, so solutions inducing subcritical non-degenerate initial data on the singularity are stable. Right? You take any such solution inducing subcritical non-degenerate initial data on the singularity along a CMC foliation, you perturb the corresponding initial data, then you're going to get another solution with the same property, right? It's going to also induce subcritical non-degenerate initial data on the singularity. You can also use these methods to get stability of degenerate background solutions, but in that case, then you get weaker asymptotics somehow. I mean, so these data on the singularity, at this point, we only get that for in the non-degenerate setting, right? So, okay, and then, I mean, so this result also sort of contains previous results in the CMC setting somehow. But again, I mean, you only get these detailed asymptotics in the non-degenerate setting, right? Okay. Right. So now, I mean, one disadvantage of the result is that we're using the CMC setting, meaning that we cannot localize in space. And since the causal structure is such that things localize, you would expect it to be possible to localize. I mean, just like Florian and Todd have done. But you can also get this type of result in the localized setting. And this is a recent result just a few weeks ago by Andrés Grisales. So in this case, you get complete asymptotics under general localized assumptions. So again, the argument is local in space. The assumptions only involve bounds on the expansion normalized quantities and non-degeneracy conditions. And the conclusions include that you get data on the singularity, right? So this is, and in this case, the gauge is such that you only have hyperbolic equations. I mean, you only have evolution equations, right? There are no elliptic equations here at all in this setting. Right? And in particular, one consequence of this, of the lapse, or of the gauge choice, well, actually so one consequence of the gauge choice is that this t theta -1 is actually going to converge at a rate. So that's one consequence of the gauge choice. And once you know that this is going to converge like t raised to delta, where delta is something positive, you see that this factor in front of n is integrable. And so this means that n is going to converge to something which is non-zero, right? And then you notice that this capital theta goes to 1. This means that the little theta goes to 1/t. It behaves like 1/t, right? So it synchronizes, this choice of gauge actually synchronizes the singularity to occur at t = 0. Okay, so this was the last point on my list of advantages of this notion of initial data on the singularity. Now I'm going to go back to the first point again, since I have a little bit more time, it seems. So I was saying that there is a geometric initial value problem for data on the singularity in this sense. So here I'm just going to mention actually a result again, Andrés Franco Grisales. He should be giving this talk, right? Anyway, so this is in 3 + 1 dimensions, right? So here you start with initial data, so non-degenerate initial data on the singularity in the way I described before, right? And given initial data on the singularity, and this is in the smooth setting, I should say. So this is in the smooth setting. Then there is a corresponding development with a Gaussian foliation. So lapse 1 shift 0, right? That with the following property then. So you get this Lorentz metric, and you also get a scalar field on this manifold. And then mg phi will solve the Einstein scalar field equations. The mean curvature is going to blow up uniformly in the direction of the singularity. And if you look at the expansion normalized data on the constant T hypersurfaces, they will, in the limit, induce the prescribed data. So in this sense, corresponding to data on the singularity, there is a development, right? Okay. So roughly formulated, given initial data on the singularity, there is a locally Gaussian, globally hyperbolic development of the data. So close to the singularity, you have a Gaussian foliation, and the solution then converges to data on the singularity along this foliation, right? But then you can sort of upgrade this to a more global statement. Namely, if you take initial data on the singularity, there's actually a maximal locally Gaussian globally hyperbolic development, which is unique up to isometry, right? So you get a unique global object starting with this data on the singularity, right? So this is nice. So there is a geometric initial value formulation with data on the singularity, and there are corresponding solutions. Okay, so that was point number 1 on my list, I suppose. Point number 2 was that it gives this notion of data on the singularity gives a unified picture of previous results starting with data on the singularity. So there's a large body of results already where you start with data on the singularity and then prove that there are corresponding developments. So this is not the first result. And this is certainly, here I've listed some results in the absence of symmetries. This is not in any way meant to be exhaustive. But so one important result from 2001 is due to Lars Andersson and Alan Rendell, right? So in this case, they looked at the Einstein scalar field, Einstein's stiff fluid equations, and they were in this is in the 3 + 1 dimensional real analytic setting, and they were in some sense putting data on the singularity, proving that there is a corresponding development. Then there's a year later, this was generalized to higher dimensions. And there was a little bit of a renaissance then later on. So Paul Klinger, he proved in the real analytic setting, in the real analytic vacuum setting, in 3 + 1 dimensions also, that there are solutions corresponding to data on the singularity. And this was improved in several ways by Greg and Jonathan. So in that, I mean, this was restricted in certain ways. So this is sort of the full range of Kastner exponents that you would expect. And this is in the smooth setting, right? Where you now have data on the singularity in the vacuum setting. So now this condition 4, if you remember, in the definition of geometric data on the singularity comes into play, and it's important here because these data here cannot be subcritical, right? They cannot be. It's impossible somehow. That's prohibited. And then there's a localized version of this result, and I'm sort of marking this result by Greg and Jonathan in red here because this was sort of methodologically was important for Andres Franco Grisales in his work. Okay, so these are some, but the point here is now that all of these results, okay, I mean, in the second case, I haven't worked out with the Yang, Mills, and Dilaton and Maxwell and whatnot, right? But I mean, for the Einstein scalar field setting, vacuum setting, I mean, you can interpret all of these results as inducing data on the singularity in my sense of the word. And it's also of some interest to note that there are data on the singularity, I mean, so that Andres deals with that does not fall into this category and that does not fall into this category, right? So there, it's in that sense, it's actually generalizes, right? There's also, I mean, there's also a large body of work in a spatially homogeneous setting, and this is an even, I mean, I've omitted even more results here. But again, I mean, for the cases that I've looked at and worked out, all of these results are special cases, right? They all, you always get data on the singularity in the geometric sense of the word. And just I think it's, I mean, of some interest to illustrate how different the previous notions of initial data on the singularity were. So, I mean, these previous results, even though I say, well, you start with initial data on the singularity, get a corresponding development, the notion of initial data on the singularity that people were using were quite different from result to result. So I'm just going to give you 3 examples here so you get a flavor for what type of notion of initial data on the singularity people used previously. So if you ask Lars Andersson and Alan Rendell, right, what is initial data on the singularity? For them, initial data on the singularity, and I don't know if they exactly thought of it that way, but for them, initial data on the singularity is a solution to the so-called VTD equations, so the velocity term dominated equations, right? So what are they in this setting? Well, you look at Einstein's equations in a Gaussian foliation, so lapse 1, shift 0. And then what is this thing? Well, this is actually the Hamiltonian constraint where we just set the spatial scalar curvature to 0. And in the energy density here on the right-hand side, you've actually also just thrown away all the spatial derivatives. I mean, and this was an analogy what Warren was saying this morning, right? Funny enough, in the momentum constraint, you keep all the spatial derivatives. And this is actually very important. You have to keep all the spatial derivatives here. And then in the evolution equations, you just drop all the spatial derivatives. And here, I mean, there are some things that I'm sort of omitting here. So here in the energy density, you drop the spatial derivatives. In the current here that goes into the momentum constraint, you keep the spatial derivatives. But here in this part of the stress energy tensor, you throw out all the spatial derivatives. So this is what they start with. This is data on the singularity for them, a solution to the VTD equation, and it also has to satisfy subcriticality conditions. So given a real analytic solution to the VTD equations satisfying the subcriticality condition, the statement is then there exists a solution to the actual equation, so a real analytic solution to Einstein scalar field equations asymptoting to this VTD solution. That's, from their point of view, this is how what the data on the singularity are and what the relation between data on the singularity and the development is. If you go now, so this I suppose this may have been one of the earliest results on starting with data on the singularity. This is the one by Kichinasamy and Rendell. This goes back to 1998. So they were doing this in the Gaudi setting, and now you know already the Gaudi metric, right? So So what is data on the singularity in this setting? Well, data on the singularity in this setting is, well, okay. So it's these functions k, phi, x0, and psi. This is data on the singularity. And they should satisfy some condition here, namely this condition. So given k, phi, x0, and psi, satisfying this condition, there is a unique solution to the Einstein vacuum equations of this form, such that capital Z and capital X have these asymptotic expansions, right? So this is now the statement, the relation between data on the singularity and solutions, right? And now, so here is the result by Greg and Jonathan. They can correct me if I'm misinterpreting them. So in their case, the initial data on the singularity are Cij, so these are functions that will appear in the metric in the end, and the Pi's, which are effectively the Kastner exponents, right? So given these functions satisfying these conditions, there is a corresponding development, right? Okay. So if you look at these, so these were 3 examples of data on the singularity, right? And it's not completely obvious what the relation is between these different data on the singularity, right? But what I'm telling you is that all of these examples, they all induce data on the singularity in the geometric sense of the word that I described previously, right? So this is all, I mean, these are all special cases of solutions inducing data on the singularity. So it gives a unified picture to these things. Okay, then I was thinking of perhaps saying something about how you can use this notion of initial data on the singularity to produce conjectures concerning the asymptotics, and also to give a unified picture of the results in symmetric settings. But I think my time is up, so I think I end here then. Oh.
I think it's okay. Want to go 5 minutes?
Okay. Let's.
Unless you were looking for an excuse.
No. Okay. So let's just return. Let's just apply this as in a simple case, in this Bianchi spacetimes, right? In a spatially homogeneous setting. So now I just wrote down the definition of initial data on the singularity again, but in this case I wrote it down in 3+1 dimensions, and then this 4th condition simplifies a little bit, and it's that this OABC vanishes in the neighborhood of X if PA of X is less than or equal to 0 and ABC are distinct. So now just for the fun of it, let's apply this notion of data on the singularity in the spatially homogeneous setting. And that's, for the sake of argument, we take unimodular 3-dimensional Lie groups. This is so-called Bianchi class A. Okay. Now in this case, these conditions, these are just algebraic conditions. You can work it out. It's just algebra. Okay. It takes a little while, but it's just some algebra, right? To work out what the data on the singularity are. And the picture you get in the Bianchi class A setting is this. So if you look at this, so I've now, since these exponents, the pi sum up to 1, it's natural to summarize them in this way, right? By this sigma plus and sigma minus. So, and then in this setting then, if you go back to this condition, I said the dangerous part is when these eigenvalues are less than or equal to 0, right? Okay. And in this picture, when all the eigenvalues are strictly positive, that's this triangle here. So inside the triangle, all the eigenvalues are strictly positive. This is the good part, right? So that's you always have data there, right? So that's nice. Bianchi 1. So in the case of Bianchi 1, this one picture describes Bianchi 1. In this case, because of the Lie algebra, all the structure coefficients vanish. So there are no structure coefficients. So therefore, this condition 4 is just void in that setting. It doesn't impose any conditions. And therefore, in Bianchi 1, you can converge to anything, right? I mean, all these things are possible. In the case of Bianchi type 2, it's like the Heisenberg group. Then there's one structure coefficient which is non-zero. And I mean, so when you go outside the triangle, here there's one structure coefficient which has to be set to 0. There's another structure coefficient over here, third structure coefficients. But here in Bianchi 2, in the Heisenberg group, there's one structure coefficient which is non-zero, which means that there's one part which is prohibited, right? In 6-0, this is the solvable Lie group, and 7-0, this is a strange subgroup of the isometry group of R3. So then there are two structure coefficients which are non-zero, so these are prohibited. And in Bianchi 8 and 9, all the structure coefficients are non-zero, so all the regions outside the triangle are prohibited. So now you would conjecture, well, what should solutions do? Well, they should converge to data on the singularity, right? And this is what happens. So you can prove then that this is what happens. And this is actually non-trivial, because if you would look at this Bianchi 8 and 9 case, and if you start close to vacuum, the solution can bounce around any amount of time along the Kastner maps and look pretty chaotic, that sooner or later, the contribution from the matter is going to start to dominate. You're going to end up inside the triangle. You're going to converge there. And you're going to induce data on the singularity. And that's it. And in fact, in this setting, you can even prove that there is a diffeomorphism between isometry classes of developments and isometry classes of data on the singularity. This is the best you could possibly hope for, right? I mean, it really gives a very nice characterization of developments, this data on the singularity. And this also, I mean, this picture also is meaningful in the vacuum setting. So in the vacuum setting, then you have to take the intersection of the gray area with the Kastner circle. So the circle here is the Kastner circle. So here in the Bianchi type 1, the entire Kastner circle is allowed. And I mean, this circle is represented by the Kastner solutions. In the case of Bianchi type 2, you have this segment, and Bianchi 60 and 70, you have this segment. And again, solutions converge to data on the singularity. You get a diffeomorphism from isometry classes of development and isometry classes of data on the singularity. And in the case of 8 and 9, I mean, these T1, T2, T3, these are the so-called Taube points. These are the solutions where you get Cauchy horizons. And here you have actually, this is where you have degeneracies, where eigenvalues coincide. But you see, there are no non-degenerate data on the singularity in 8 and 9. So the solutions, there's nothing for the solutions to converge to. So they should be oscillatory, and they are oscillatory, right? So you can, okay. And you can also use this intuition to get a feeling for what the asymptotics of Gaudi spacetime should be, but maybe I